on homework 6.5, I'm going to skip A and B. The graph is very simple to make. Realize that the slope of that graph is going to be the spring constant. The y-axis is the force, the x-axis is the displacement, slope, rise over run. That force divided by the displacement is going to give you the spring constant. So just go do that. C is where it starts to get a little bit tricky. I've got all the different stages of this problem drawn up here. This is when the spring is just hanging out. It hasn't been dropped. It's not oscillating. It's just resting there. Here we pick up the spring, let it go. So at some point, it's going to be in equilibrium. We don't know how far that is. We don't know how fast it's going right there. We'll find that later. And then later, it's going to stretch out to 1.5 meters, and it's going to stop. It's asking what the mass is of that little ball that's going back and forth. This is something falling. There's a spring involved. There's motion. This is textbook conservation of energy. So this is our initial spot. It starts here. And this is our final spot. It starts here. Now, we don't know where the ground is, but we're going to say that this right here, for this part of the problem, is zero gravitational potential energy. That's our ground, which means it starts off above that by 1.5 meters, so it's going to have gravitational potential energy right there. So we can go ahead, write out our big formula. This is a totally wrong order. At the beginning, we say it does have gravitational potential energy. It starts out up here, but it's not moving, so we don't have that. The spring is not stretched out yet, so there's no elastic potential energy. At the end, once it gets down here and stops, there's no kinetic energy at the end. The spring is stretched, so we leave that. And then we said that right there was zero gravitational potential energy, so that goes away as well. We expand, mgh initial equals 1/2 kx squared. K is a number that you found from doing the graph and doing the slope. N you're trying to find, h initial is 1.5 meters, the difference from here and here. X is the amount that the spring stretches out. So that right here, that spot over there, the 0.6 meters, that's like the default length of the spring. And then it stretches from here down to 1.5. So this X is going to be 1.5 meters minus 0.6 meters. So we get 0.9 meters that we're going to plug in for X right there. Plug all your numbers in, do some rearranging, and you end up getting that the mass is 0.66 kilograms. We're going to use that for later. I'll write it over here for now. So that's part C. Part D, what does part D ask? Part D asks what the force is in the cord when the spring is at equilibrium, so when it's hanging out right here. Now, by now, you should be able to just vomit the definition for equilibrium in your sleep. Forces are balanced. That's always true. So right here, there's only two forces acting on it. There's the spring force pulling up and the force of gravity pulling down. At this point, we know both of those are equal. Acceleration is 0. So we can say the force of the spring that we're trying to find is equal to Fg, which we know is mg. Well, we just found the mass at 0.66. We know the gravitational field strength on Earth. So our force is going to be 0.66 times 9.8. Force of the spring is 6.5 newtons. That's D. Done. That's Di, excuse me. D2i. Determine the stretch right here. So now we're trying to find how far does this stretch past the default, past that right there. Well, anytime we're talking about how far a spring stretches, we have two options. We can do Hooke's law, F equals kx, or we can do energy, 1/2 kx squared. The problem with Hooke's law, the force is changing throughout here. So unless you know calculus, you can't do anything there. We do know about energy, though. We can do a conservation of energy setup from that initial spot to that final spot. Or, excuse me, from that initial spot to that final spot. Now, what we're going to do is say that this location right here is our zero gravitational potential energy. You'll see why in just a sec. Be right back. Okay, I'm back. I realized I did something stupid. I was answering the wrong question. 2i asks about that stretch. I told you we couldn't think about forces because that was changing. However, I forgot what I had just said. Those two forces are equal. We know what the force is. So right here, that force is 6.5 newtons. The answer we just found in part I. This force of the spring expands into kx. You know what k is. You found it in part B. solve for x. You end up getting x is 0.27 dear God, meters. So that right there, 0.27 meters. So now we know all the links we need to know, and we can move on to 3i. This is the part that's asking you to find velocity, and this is where you want to set this as your 0 point for gravitational potential energy. This is no longer our 0. That's our 0. So, conservation of energy, we start out up here. We're going to end right here. Same basic equation. We go through and cross stuff out. At the beginning, it's not moving. The spring is not stretched. At the end, it is moving because it doesn't stop until it gets down here. It is not at 0 because we said that that point was gravitational potential energy of 0. And the spring is a little bit stretched relative to a totally unstretched link. So the spring is storing a little bit of potential energy right there. So we can't cross that off. At the beginning, we have M, G, H. We know mass, we know gravitational field strength. H is from here to here. That's going to be 0.6, our default length, plus the 0.27. So we know that this is our H. Okay, final, 1/2 mv squared, so the velocity right there. We don't know the velocity, we're looking for it. We do know the mass, we found that earlier in the problem. Equals 1/2 k, which we still know from part B, x, which we just found was 0.27. You can plug all of this in, do some rearranging, solving, and you get that the velocity at equilibrium, the final velocity for this problem, is 3.8 meters per second. And then part IV doesn't actually ask you a math problem, it's a concept problem. It asks, is that the maximum velocity for this oscillation? Now, something you should know and be familiar with is that at equilibrium, it's always going to be going to maximum velocity. As it's bouncing back and forth above and below that spot, it stops, 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 but in the middle, it's going the fastest. That's where the forces are balanced out. The gravity is still pulling it down. The spring force hasn't started pulling it back up yet, so it's moving the fastest right there, and then if it keeps going, it's going to slow down to 0, speed up to maximum, slow down to 0, speed up to maximum, slow down to 0, forever and ever and ever. So that's the answer to part 4. Just put that into words somehow, answer it. And this is another one of those really good examples of simple harmonic motion just being another variation of conservation of energy. But now it just happens again and again and again. Ask any questions on Emmoto. See y'all tomorrow.